So in the last video, we were introduced to MergeSort, and we actually walked through the process of how we would go ahead and sort this list of 8 items. And we saw how we broke it up, and then we would slowly bring it back together. Well, I want to go ahead and highlight a few more things about MergeSort, and then we're going to talk about the running time. So I wanted to split this up into 2 videos. So we're looking at MergeSort right now, and I will go ahead and rewrite all this and make it nice and neat again. But one thing I want to highlight is when you have a recursive algorithm, which means an algorithm that's going to call itself. The danger of doing that, not really danger because we're always going to have this condition that I'm going to mention, but something we need to look out for is the function is going to call itself, and that means it is going to repeat from the start. So something has to happen where the function will know it needs to stop at some point, because if it just goes on forever, well, that's a little bit of a problem. So it needs to know it's going to stop at some point, right? If you have an algorithm to make sandwiches, and let's say you have infinite bread, infinite turkey, and infinite mayonnaise or whatever, then if at one point you know that you need only 7 sandwiches or 8 sandwiches, but you never tell it to make less sandwiches, right? Or stop when you reach this point, well, you're going to have so many freaking sandwiches. That's going to be a problem, right? I'm not eating them all. So you need to have something called a base case. And the base case is going to be essentially when you stop, right? We know right here, as soon as n is equal to 1, well, we're going to stop going back to this section over here with all the recursive calls. So once we reach that point right here, right? When n is equal to 1, and where was that down here, right? If we look all the way down here, we can see over here, once we had these set up over here, right? This is n equal 1. This over here is n equal 1. All these here are n equal 1. So you reached your base case over here, which means now you can focus on the rest of the algorithm, right? You can stop worrying about calling yourself over and over and over because you reached that base case. So to reach the base case, you obviously have to have a base case set, but you also have to be making sure that you are calling all this over here, you're calling it on a smaller division of the information, right? We're not calling it on, this is the original information, right? This is the original. And here we're calling it on half the information. So this is half. And this over here is another half. So that's one thing we have to consider, and we're going to take a look at that. So I want to go ahead and clean up over here. So let me go ahead and get rid of this. What did I just do? Okay, I realized I was drawing on 2 different layers. It's not a big deal. I can just go ahead and scroll up on this one. So we're going to talk a little bit more about MergeSort. We're going to talk a bit more about recursion, and it's all going to come together. So what are the important things we need to look at when we're talking about recursion, right? The important things for a recursive algorithm, we're going to have some, I guess you can call them conditions here. I'm not selected on the layer. There we go. So for a recursive algorithm, we need to know, does the algorithm terminate? Terminate. And this could be done, well, it will be done by having a base case. And calling recursion on smaller and smaller pieces of information. Or a correct term I should probably use are inputs, /inputs. Right? If you have a point where you're going to stop and you're always approaching that point every time you pass through, well, naturally, you're going to end at some point. So that's one thing. That's the most important thing we want, right? Another thing for recursion is the algorithm correct, right? Is the algorithm That's always important as well. We want to make sure, does it give us what we want? In the last video and also in the start of this one, we saw actually walking through with a list of 8 elements, we saw that we actually did arrive at the answer we want. So yes, the algorithm was correct. But having those 2 things, is that enough? If we know our algorithm ends and we know that it it's correct, it's going to give us the right answer. Are we done? Well, we talked about this in the first video of the series, if you watched it, where I said that if we want to sort 4 numbers, what is the most childish way we could possibly do it? And that is to write out every single possible outcome. And that would take forever. We saw that would take so long. And we don't want that. So one thing that is really crucial, which most of what these videos are going to be about, which is how to what the runtime of these algorithms are and how we can optimize them, is going to be, is it efficient? What is the runtime? Is the algorithm quick? What is the runtime? Is there a better way to go about solving that algorithm or solving that problem, right? The one where we would just go ahead and we would list every single possible ordering of, say, 4 or 5 numbers and then pick the one that was right, the one that was ordered. That's really not efficient at all, right? It does satisfy the first 2 conditions, but just because it did the first 2 doesn't mean that we should ever use it. We want to make sure that we are always picking quick algorithms, and that's something that is going to be tricky. It's going to be difficult to assess, but we are going to do it. I think I'll cut this video short and I'll go into the next one where we're going to be assessing the runtime of the MergeSort algorithm. So we'll start fresh. So if you were still a bit confused with MergeSort, the next video should clear some things up for you guys. So I'll see you guys then.